In this video, we solve problem 6.3.6 from Nagle's Fundamentals of Differential Equations 7th edition. We're asked to find the general solution to the given equation. We see that the corresponding homogeneous equation has constant coefficients and that the right-hand side, after all the y's are moved to one side and the functions of the independent variable only are moved to the other. The functions of the independent variable only are non-zero. So that means this is a non-homogeneous equation, and that means that we need to solve this in two parts. So the first thing that we need to do if we want to solve an equation like this is solve the corresponding homogeneous equation. And then we'll say, okay, what about y sub p? How do we find the particular solution? So we look at the right-hand side and we say to ourselves, is this a finite sum or finite product of exponentials, sine and cosine, or polynomial functions? And it is. It's a constant times an exponential plus a sine function. And then we also say, is the left-hand side an operator applied to y, where all of the coefficients are constants? Is the corresponding homogeneous equation a constant coefficient equation? And it is. Since both of those are satisfied, we can solve this with the method of undetermined coefficients. Now you could also use variation of parameters, but I recommend using the method of undetermined coefficients when you can. So that's the plan, but first we need to find y sub c. And that requires solving the corresponding homogeneous equation. The corresponding homogeneous equation looks like this. Just set that right-hand side equal to 0, and then we say that has constant coefficients. So let's let y equal e to the mx. And since it's a third order differential equation, we're going to compute y prime, y double prime, and y triple prime. Every time you take a derivative, you're going to multiply by an extra m. It's due to the chain rule. Derivative of e to some power is e to that power times the derivative of the inside, and the derivative of m times x is m. Okay, so that's the form of our solution. And we're assuming that y equals e to the mx is a solution, of this differential equation. If this is a solution, then we should be able to substitute all of these functions into this equation and we would get something that is true. So let's substitute. Y triple prime, which is m cubed times this exponential, minus y double prime, m squared times the exponential, minus 8 times y prime, that's m times the exponential, plus 12, times our original guess, y equals e to the mx. And so if y equals e to the mx is the solution of this equation, then m must satisfy this algebraic equation. Now we can factor out an e to the mx from everything. And if this times this equals 0, that means one of the factors is 0. But exponential functions are never 0. So that means our polynomial must be 0. And that is called the characteristic equation for this particular differential equation. Okay, now that I've got my characteristic equation, I need to find values of m that cause this equation to be true. So what we're going to do is use what's called possible rational roots. And our list of possible rational roots comes from taking the factors of the constant term and our constant term in this case is 12, and dividing by the factors of the leading coefficient. There's an implied 1 there. So factors of 12 include plus and minus 1 and plus and minus 12, plus and minus 2 and plus and minus 6, plus and minus 3 and plus and minus 4. And then we're going to take all of those and divide by plus and minus 1. But dividing by positive and negative 1 doesn't actually change any of the values on that list. So we've got quite a few possibilities. 1, 2, 3, 4, 6, and 12. Those might be values of m that cause this equation to be 0, or that cause this expression on the left-hand side to equal 0. Or we could substitute in the same values but negative. So we do have a lot of possibilities here. It looks like we've got 12 of them. We've got 6 pairs, so we've got 12 of them. But at least we are not guessing from infinitely many possibilities. At least we've got it narrowed down to these 12 as far as the possible rational roots are concerned. So you just ask yourself, like, well, which of these values do you think will actually work here? I always try 1 first if it's on the list. If m equals 1, I'd have 1 minus 1 is 0. And then I'd have a negative 8 plus 12, that's 4. So 4 is not equal to 0, so that doesn't work. What about negative 1? If that was a negative 1 for m, let's see if that would work. So basically what we do is we're trying to factor this characteristic equation. We list the possible rational roots. And then we try values of m on this list until we find a root. And I like to try small values of m. So we have negative 1 cubed minus negative 1 squared minus 8 times negative 1 plus 12. So that's negative 1 minus a positive 1 plus 8 plus 12. Well, that's 20 minus 2. It's not equal to 0. So m equals negative 1 is not a root. What about 2 or negative 2? Let's try 2. So I've got 2 cubed minus 2 squared minus 8 times 2 plus 12. So that's 8 minus 4 minus 16 plus 12. Yeah, I think that's going to work. 8 and 12 is 20, and negative 4 minus 16 is negative 20. So I have 20 minus 20, which is 0. So m equals 2 is a root of the polynomial, or a 0 of the polynomial. And that means that m minus 2 is a factor of the polynomial. So that means that this expression here can be written as m minus 2 times some polynomial q of m. We just need to find q of m. Well, if this is equal to this times this, that means q is equal to this divided by that. So let's write that down. Okay, so this equals this, where q is equal to that. All right. So now we just have to do this division. So we'll use synthetic division to find q. And that's actually pretty easy. You just set this m minus 2 equal to 0. You get m equals 2. That goes in a little box. And then you list the coefficients of q right here. Q has, or excuse me, not the q, the polynomial in the numerator. The coefficients are 1, negative 8, and 12. Now, if there were any missing terms there, if, let's say, an m² was missing, we would add in a 0 times m². So we'd have a 0 there. but they're not any missing terms. We've got an m cubed term, an m squared term, an m term, and a constant term. So those are the coefficients on our list. Bring the 1 down, multiply, and add. Multiply, and add. Multiply, and add, and that's great. We get a remainder of 0, which is what we should get because m equals 2 is a root. So that means that these are the coefficients of q of m. So our polynomial is m minus 2 times q of m, where q has coefficients 1 and -6, and this was a cubic polynomial divided by a linear polynomial. A cubic polynomial divided by a linear polynomial is going to be a quadratic polynomial. This is 1m squared plus 1m minus 6 times m minus 2, and that equals 0. And this factors, I need two numbers that multiply to give me -6 that add to +1. 3 and 2 will work if they have opposite signs. That's a +3 and that's a -2. That'll work. And then I look at this and I have an m minus 2 twice. So I'll write that as m plus 3 times m minus 2 quantity squared equals 0. So either m plus 3 equals 0 or m minus 2 equals 0. And if we subtract 3 from both sides, we get m equals -3. If we add 2 to both sides, we get m equals +2. All right. Now, m equals -3 is the 0, or the root, that corresponds to that factor, and it's raised to the first. So we just have m1 from that factor. But this is an m minus 2 squared. It has what's called multiplicity 2. So m2 is equal to 2 and m3 is equal to 2 because it's an m minus 2 factor that appeared twice. So that means our corresponding solutions are y equals e to the mx. So y1 is e to the m1x, and y2 is equal to e to the m2x. m2 is 2. And then y3, since that's a repeated root, looks just like that one, but you multiply by an extra x. Okay. Oops, not the general solution, sorry. The complementary function or complementary solution is c1y1 plus c2y2 plus c3y3. So this is c1 times e to the -3x plus c2 times e to the 2x plus c3 times x times e to the 2x. All right, so we found the complementary function. And I didn't write out all my steps, but remember how we did it. We let y equal e to the mx, we took the derivative 3 times. We substituted into the equation, we got a characteristic equation. We need to factor that somehow. If it doesn't obviously factor in an obvious way, then we go to possible rational roots. Then you just try values on this list until you find the one that works. I tried one that didn't work. So then I tried a different one and it did. So once I found a root, said m equals 2 is a root, so m minus 2 is a factor. Then I said, okay, well, it's this polynomial is this times something. To figure out what that something is, I need to divide this factor out. So I'm going to take my polynomial that I started with and divide by the m minus 2. And whoops, it's a different problem. So to do that, we did synthetic division. These are the coefficients of the polynomial q. They're right there. And then this was quadratic and easily factorable, so we wrote it in this factored form. And then we simplified. So we've got our factored characteristic equation now. And then we found 3 roots, m1, m2, and m3. Those corresponded to 3 linearly independent solutions, y1, y2, and y3. And then y sub c is c1y1 plus c2y2 plus c3y3. All right. And now we want to go back to the original differential equation and find our y sub p. Okay. Now with this, We always start by looking at the form of the right-hand side and then writing down our educated guess. We're never 100% sure that this is going to work. But if we compare our educated guess to the functions that satisfy the corresponding homogeneous equation, often we can modify our guess before we even try it to get one that's most likely to work. So first, let's say we're going to try y sub p equals this. Well, that's a constant times e to the negative 2x. And then for that piece, that's what I would guess. And then for here, I've got a constant times sine of x. Since constants times sine of x and constants times cosine of x could potentially give me a sine of x, I need two terms. I need a b times sine of x, and I need a c times cosine of x. Okay, now before I go further, I need to look at this and compare to this list. I say to myself, are there any constants times e to the negative 2x that would satisfy the original equation? And no, there aren't any e to the negative 2x's on this list. We've got an e to the positive 2x. That's fine. Doesn't conflict with this e to the negative 2x. Are there any sine or cosine functions? Nope. So our initial guess is going to work. Now, if there was something on this list in our terms for y sub p that was already up here, we would want to multiply the guess that corresponds to that piece by x as many times as possible, or as many times as necessary, excuse me, so that the guess, or the part of the guess that corresponds to that term on the right-hand side, is not on this list up here. But we're not in that case, so we're just going to find a, b, and c with our initial guess. So we're assuming that y sub p has this form with coefficients a, b, and c to be determined by us. That's why it's called the method of undetermined coefficients. So to find those coefficients, we assume that this works. We take the derivative 3 times and we substitute into the differential equation. So we need to compute y sub p prime and y sub p double prime, and since it's third order, y sub p triple prime. This is not too bad at all, because we've got a constant times e to the negative 2x. Easy to differentiate that. You bring the constant down. The derivative of e to some power is e to that power times the derivative of the inside. And then you bring your constant down and you multiply by the derivative of sine of x. Derivative of sine of x is just cosine of x. Bring your constant down, and then you take the derivative of cosine of x. Well, the derivative of cosine of x is negative sine of x. So you can write minus c sine of x if you want, or you can write c times negative sine of x. Either way will work. That's our y sub p prime. Take the derivative again. Well, every time we take the derivative of e to the negative 2x, we're going to get an extra factor of negative 2. So I'll have negative 2 times this, which is positive 4a times e to the negative 2x. Derivative of cosine is negative sine, so I'll have negative b times sine of x here. And the derivative of sine is cosine, so I'll have negative c times cosine of x there. Y sub p triple prime, do the same thing again. We're going to bring our constant down, but that constant gets multiplied by a negative 2 by the chain rule, so we'll have negative 8a times e to the negative 2x. Derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. A negative times a negative will give us a positive, so we have that right there. So we're assuming y sub p satisfies this differential equation for some values of a, b, and c to be determined by us. To find those values of a, b, and c, I'm going to substitute all of these guys into the differential equation and simplify and set the result equal to the right-hand side. Now, there are a lot of terms here. If I take all of these and I write them all in one line, I would almost have to move my paper to landscape orientation just to show you all of the terms. So we don't want to do that. What we want to do instead is probably add vertically. That's what I prefer to do. It makes the bookkeeping a little bit easier. So we're still going to substitute into the differential equation. But when we do, we're going to add vertically, just like you did in elementary school when you said that 4 plus 2 equals 6, and you added vertically like that. We're going to do the same thing. We're just going to be working with terms in a differential equation. So we've got y sub p triple prime, and we want to subtract y sub p double prime, and then we want to subtract 8 times y sub p prime. and then add 12 times y sub p. I'm going to write all of that out over here, and then we want to collect like terms. So y sub p triple prime is this, so I'll just write it down. And I think I want to put my sine term first, so I'll put the sine of x here and the cosine of x over here. Okay, now we're subtracting y sub p double prime. So there's my y sub p double prime, but I need to multiply it by -1 before I add. -1 times that is going to give me a -4a times the exponential. -1 times this is going to give me a positive b times sine of x. -1 times that is giving me a positive c times cosine of x. Okay, and then I want -8 times y sub p prime. So -8 times this. -8 times -2a is positive 16a times the exponential. -8 times this is going to give me a -8 times b times cosine of x. And then we have -8 times this. A -8 times a -c is a positive 8c. Yep, that's times sine of x. Okay, and then we want 12 of y sub p, and y sub p is right there. So I've got 12a times my exponential, 12b times the sine of x, plus 12c times cosine of x. And then we want to add vertically. So these, when you add them together, equal whatever we get over here. Now notice that I've got a -8a minus 4a. That's -12a plus 12a is 0a. So those are gone, and we are just left with the 16a times the exponential there. Now over here, you've got sine functions. Well, looks like I've got 12b plus another b, that's going to be 13 b's. And then I've got 8c plus another c, that's 9 c's times sine of x. And then over here, let's do the b's first. We have -8b minus 1 is 9b. 12c plus 1c is 13c. Okay, and that is our left-hand side. We want to set that equal to the given right-hand side. And the given right-hand side was this, 3 times e to the -2x plus an implied 1 times sine of x. Now there were no cosines, so there's an implied 0 times cosine of x there. Now the functions e to the -2x, sine of x, and cosine of x are linearly independent functions. So that means that the only way this expression on the left-hand side could equal this expression on the right-hand side is if the coefficients are equal. So what that means is that 16a would be equal to 3, and 13b plus 9c has to equal 1, and -8 or -9b plus 13c must equal 0. So that's our 3 equations and 3 unknowns, which is going to simplify pretty quickly to 2 equations and 2 unknowns. So I've got that there. (16a) equals 3, 13b plus 9c equals 1, and -9b plus 13c equals 0. And if you're solving for a, you get a equals 3 over 16. Okay, and now we've got 2 equations and 2 unknowns, and you can get rid of the variables in whichever way you prefer. It's actually not, there's not one of them that's easier to get rid of. I've got 13b and -9b, or 9c and 13c. So we're kind of out of luck there. We're going to have to multiply by 9 and 13, or 9 or 13. What I would recommend is, let's say let's multiply this one by, let's multiply that one by 13 and multiply this second one by 9. So we'll have just these two now. 9 times 13 times b plus 9 times 9 is 81 times c equals 9. And then this one, when we multiply by 13, we're going to have negative 9 times 13 times b. And then we'll have 13 squared, I don't know what that is, times c equals 0. And when you add them together, you get this 81 plus 13 squared times c equals 9. So let's see what 13 squared is. Oh, that's right, 169, I forgot. And then we have 81 there, so we get 250, c equals 9. So c equals 9 over 250. And now that we know c, we can use that to find b, and you can substitute into whichever equation you prefer. I think I'll use the second one. So I have negative 9 times b plus 13 times c equals 0. Oops, I wrote 1, 0. I chose the last equation on that list. And 9 times 13 turns out to be 117. So this is negative 9b equals 117 over 250. So that equals 9b. And if you want to get b by itself, you need to divide by 9 or multiply by 1/9, same thing. Well, I guess that 117 was 13 times 9. So the 9s will reduce and we'll just get b equals 13 over 150 or 250. Okay, so we've got our a, we've got our b, and we've got our c. Now we just need to substitute into the form of the general solution, or the form of y sub p, excuse me. So y sub p had this form. It was a times e to the negative 2x plus b times sine of x plus c times cosine of x. Remember, that was a choice that we made earlier. That was our guess. As long as we're consistent with that guess, the a, b, and c that we just found should work. So a should equal, according to our work, 3 over 16. B is 13 over 250. And C is 9 over 250. That's our y sub p. And the general solution is y equals y sub c plus y sub p. So we have c1 e to the negative 3x plus c2 e to the 2x plus c3 x e to the 2x plus that expression there. And it wasn't too bad. It's a pretty straightforward application of the method of undetermined coefficients. We didn't even have to multiply our y sub p by any extra x's, so it's not too bad at all.